With this lecture, we are starting on chapter 11 from the text, and we'll discuss adaptive estimation, and we'll have a number of real-world applications. The outline of this topic is that in view of the models that we considered previously, they were limited because of only additive white noises both in the process and measurement with known statistical properties. What this implies is that the system model, which consists of the state transition matrix, the input gain and input, the measurement matrix, noise covariances, were all assumed to be known. In the case that noises were not white, with known autocorrelation, Chapter 8 discusses how those can be handled. But it's a much more significant problem that in many practical situations, these parameters of the problem are partially unknown and possibly time varying. There are techniques for system identification which need typically maximum likelihood approaches to come up with the identification or estimation of structural parameters of a system. We will not take this approach, but what we are going to provide as tools are state estimation techniques which can adapt themselves to certain type of uncertainties beyond those stated earlier, namely adaptive estimation algorithms. So we will not do a completely open-ended estimation, but some kind of estimation of the models as well as the states. So that would be the goal. So one type of uncertainty that we are going to consider is unknown inputs into the system. And these situations typify maneuvering targets, but there are several other applications. Another type would be a combination of system parameter uncertainties with unknown inputs, where the system parameters are assumed to take values in a discrete set. This is really the multiple model estimation approach. It turns out that even though we use a discrete set or a finite set of models, these adaptive estimation techniques are very powerful and relatively simple. So, in general, a maneuvering target is characterized by an equation of the same form as we have seen, but now the input, UK, is unknown in addition to the process noise. So we assumed in the standard karma filtering approach that UK was known. Now we have this UK also unknown. In this situation, you can use the following models. The unknown input can be modeled as a random process, namely treat it as another process noise, just have a larger process noise than the VK, or the unknown input is estimated in real time. In this case, typically it will be assumed to be constant over a certain amount of time. Now the random process type models can be assumed that they use a white noise or an autocorrelated noise model. So we have this unknown input as a random process amounts to treating it, as indicated before, the unknown input as an additional process noise and possibly requiring augmentation of the state. We discussed earlier the use of fixed level white noise to model maneuvers in the context of kinematic models. But clearly, maneuvers are of different magnitudes at different times, and they can vary to such an extent that the adjustment of the level of the process noise would be appropriate. Sometimes you have minor perturbations in the motion, sometimes you have major perturbations in the motion. So one option is a continuous noise level adjustment technique. Another one would be to use several discrete levels of noise in the filter with the noise level switching according to some kind of a rule, and this is a logic-based rule. Another approach is the use of autocorrelated or colored noise, which was or is discussed in the text in section 8.2, which we did not cover, and the approach was discussed earlier in chapter 1. It's pre-whitening the noise and state augmentation to append to it the pre-whitening subsystem. And this is now brings this into the standard category of white noise driven systems. And again, noise level adjustment can be used with this augmented system as well. Now, all these model maneuvers as random processes, and these are really approximations because maneuvers are by their nature, and in many cases the unknown inputs in the dynamic systems are really not stochastic processes. Nevertheless, these approaches can be simple and quite effective. The input estimation, on the other hand, is implemented assuming the input to be constant, so that's exactly the opposite of a random process, constant over a certain period of time. In this case, the estimation can be carried out using a least squares approach, and the result can be used in the following ways. You come up with an estimated input and you correct with it the state estimate. That's compensation. The other approach would be to augment the state, and the input becomes an additional state component which is re-estimated sequentially within the augmented state. So we have a larger state consisting of the original state and the input, and you treat the input now as part of the state. The multiple model algorithms, which are in section 11.6, assume that the system behaves according to one of a finite number of models. Namely, the system is in one of several modes or operating regimes, and these models can differ in either noise levels or in their structure. We can accommodate different state dimensions and unknown inputs. These are called hybrid systems because they have both discrete as well as continuous uncertainties. The discrete uncertainties are the structure or parameters. This is the uncertainties across models, and the continuous uncertainties are typically the additive noises within models. And this is why hybrid systems is the appropriate term for these continuous and discrete uncertainties. In general, this approach will answer the question, which is the current model that the system follows. Obviously, we need a finite number of models, which is an approximation, but it is quite successful. And the answer will never be in a hard sense, which means the answer will be probabilistic. There is no black and white, but there is a gray answer. The probability of this model is such and such, of that model is so, and we will see the details shortly. So, among these multiple model algorithms, which have been very successful, the first one is the so-called static multiple model version. Static from the point of view that the assumed models do not evolve. We have fixed models. They do not switch. There are no jumps. The system starts with a certain model, stays with the same model. So this will be the first approach. Then we have a dynamic algorithm for switching models. And we need a model for how the models are switching, and this will be according to a Markov chain. Now it turns out the dynamic algorithm will have a problem. It's not practical for implementation due to exponentially growing computational and memory requirements. The number of models, possible models, after a while is mushrooming. So there are some suboptimal approaches. One class is generalized pseudo-Bayesian, the other one is a so-called interacting multiple model estimator. Would focus on the IMM because it is an excellent compromise between how close it is to optimum and how simple it is. So it's a very effective algorithm. And then what we are going to do is present the design of an IMM estimator for a real air traffic control problem that will be discussed in detail, and there will be guidelines that will be provided for when an adaptive estimator is needed, namely when a single model based Kalman filter is not adequate. So we'll have not only a mechanism to decide how the algorithm should be designed, but which algorithm is the most appropriate for a particular problem. So we will go to the multiple model approach because it has received so much attention in the literature as well as in currently operating systems by now due to its very high efficiency in terms of the ratio of computational requirements to performance. Okay, so what are the mathematical assumptions here? In the MM approach, it is assumed that the system obeys one of a finite number of models. And in view of this, we have a hybrid system designation as indicated before, because each model has continuous or noise uncertainties and discrete uncertainties, which is the model or mode or operating regime of the system under consideration. So across models is discrete, within models is continuous. And we are going to use a mathematical framework that is by now familiar, the Bayesian framework. We start with prior probabilities of each model being the correct one, or that the system is in that particular mode, and we will come up with equations that provide us the posterior probabilities for each mode in view of the most recent data. So we start with a static case, static from the point of view that the model is fixed, no switching. Each model is dynamic, but there are no changes of the model, so this is why the overall approach is designated as static. So we have time invariant modes. The result for this is the so-called static multiple model estimator, and we should remember, as indicated before, that the model that is in effect is the same. Each model will have its own dynamics, so the overall estimator is dynamic. Just from the point of view of the model changes, it is static. No changes are assumed to take place. So the model assumed to be in effect throughout the entire process is one of R possible models, or the system is in one of R possible modes. The distinction between model and mode is a little bit subtle. Even if I will try to keep it straight, it's very hard. Model is the mathematical model, mode is what the system is doing. So M is one of the R set of models, Mj, J going from 1 to R. And because we are in a Bayesian context, there will be a prior probability that Mj is correct, or that the system is in mode J, and this is going to be P of Mj given Z0, the initial data, the prior information, is mu J of 0. So probability, I'm using the notation mu for probability mass. This is a discrete probability for model J at time 0. Obviously, we have to have the sum of all the probabilities J from 1 to R at time 0 as well at a later time to be unity. So the correct model is among the assumed R possible models. It is a question whether a finite number of models can characterize a realistic situation. It turns out that based on practical experience, it is possible, and even with a relatively small number of models, to characterize the behavior of a system with different patterns or different regimes. At this point, it will be assumed that all the models are linear Gaussian. We can use these for nonlinear systems via linearization. The crux of the approach will rely on likelihood functions in updating the mode probabilities, and those likelihood functions will be, as discussed in the Kalman filtering case, the likelihood function of a filter is the probability density function of the innovation. And this, in the absence of any other information, will be considered Gaussian. So we will follow the linear Gaussian approach. Clearly, it applies to other cases, but they have to be taken on an individual basis to see how good these assumptions are. After that, the completely dynamic situation where the models switch or we have mode jumping would be considered. And in this second case, the system undergoes transitions from one mode to another, and the resulting estimator will be a dynamic multiple model estimator. Now, the static multiple model estimator for fixed model is obtained as follows. We will use Bayes formula, and we will calculate the posterior probability of mode J being correct given all the measurement data up to time k, and we'll develop the following recursion. Mu J at time k will be the probability that model number J is in effect given all the data through time k, and remember this is a static, no jumps among the models. So Mj has no time index. Later, in the fully dynamic case, we'll have a time index on the model. So this is the probability that Mj is in effect given, and we decompose the cumulative set of measurements through time k into the last, that little z at k, and z cap z super k minus 1. So this is the past data, this is the latest data. And we use Bayes formula to switch between Mj and zk, because zk is in general a continuous valued random variable. The observations are continuous valued. When we use Bayes formula, this is one of those mixed cases. This is an event, this is a random variable. So the probability of the event given these random variables is the probability of my random variable zk, the latest measurement, given the past data, which stays in the conditioning. This zk minus 1 is a common conditioning in every expression here. So we switch zk now given mj and zk minus 1 times the probability of mj, the model in effect being number j given the past data, divided by what amounts to the normalizing constant, that's p, the pdf of zk given the past. And we can rewrite this denominator as the sum of exactly the same terms as we see in the numerator, where we change the j to a running index I and we sum over I from 1 to r. The rewriting of the denominator from the first line into the second line is using the total probability theorem, again with the common conditioning zk minus 1 here. We can take this equation and rewrite it in a slightly more compact fashion, saying that mu jk is the likelihood function pzk given zk minus 1 nmj, and we'll see this is the likelihood function of a filter based on model number j, times the probability of this model number j at the previous time instant divided by the normalizing constant. So this is a recursion that, starting with the prior probabilities, can be iterated one step at a time and gives us the updated probability of model number j being the correct model based on the cumulative set of data. So, as indicated, the first term on the right-hand side in the above equation is the likelihood function of mode j at time k. This is the likelihood function of mode j at time k, PDF of the measurement given the mode and the past data. That's the likelihood of the mode at time k, which under the linear Gaussian assumptions is given by the same expression as we have seen in chapter 5, equation 5 to 6, 7. So lambda jk, the likelihood function of mode j at time k, is the PDF of the measurement z at time k given the past and mode j, which is the PDF of the innovation nu j at k. That's a Gaussian argument innovation, mean 0, covariance sjk, where nu j and sj are the innovation and its covariance from the mode matched filter corresponding to mode j. So we can see from this equation immediately that these likelihood functions indicate that what we will have to construct to implement this Bayesian update of the mode probabilities are mode matched filters. For each filter, for each mode we have a filter, and for each filter we will have an output which is the likelihood of that particular mode. Again, in a nonlinear and or non-Gaussian situation, the same Gaussian likelihood functions are typically used, even though they are clearly approximations. Thus, a Kalman filter matched to each mode is set up yielding those mode conditioned state estimates. So mode matched filters yield mode conditioned state estimates and mode conditioned covariances. And the probability of each mode being correct, these are the mode estimates, is obtained according to our base formula based on the likelihood function of the corresponding filter, let's say for mode j, relative to the other filter's likelihood functions. So what we have here is the likelihood function of filter number j at time k relative to everybody else's and its own likelihood function at the same time. And obviously they are weighted by the prior probabilities. Again, in a nonlinear situation, the filters really will be extended Kalman filters instead of Kalman filters, and as usual the caveat holds that one has to be careful in using this, but in pretty much all the situations the innovations are modeled as Gaussian, even if they are only approximately so. And here is the flowchart of this modular estimator, which is really a bank of filters. Here we have a filter matched to mode 1. Here we have a filter matched to mode 2, or model 1 and model 2. We assume two fixed models here. They are initialized with some initial state estimate and some initial covariance, same one for everybody. Each of them gets the measurement at time k and puts out with its own internal recursion of a Kalman filter a state estimate x hat 1 kk and its covariance, assuming the model is and has been number 1 from the very beginning. Similarly for the output of the filter matched to mode number 2. In addition to this, they all provide a likelihood function. It's a lambda 1k and a lambda 2k. These two likelihood functions go into the mode probability update box, which puts out the probability of each mode or model at every time, given the data up to that time. And then we can carry out a state estimate and covariance combination by taking these means and covariances with these probabilities using the mixture equations discussed in Chapter 1 and coming up with a combined state estimate and a combined state covariance. So the output of each mode match filter is the mode condition state estimate, x hat 1 and x hat 2, its covariance, and the mode likelihood functions to be used in the mode probability calculations. And as you notice, these filters operate completely separately. They use the same data, but they don't talk to each other at all. And this will be the major difference between this static situation, again static in terms of not time varying modes, and the other algorithm, the IMM estimator, which has interaction. The filters do exchange information, and they can handle, in view of this, time varying modes or jumps. So as the filters are initialized, they will run recursively on their own estimates, and the likelihood functions are used in the mode probability updates, and the latest mode probabilities are used to combine those mode conditioned estimates and covariances. Here is the way those estimates are combined, because we made an assumption that the PDF of the state is a Gaussian mixture with R terms. The PDF of x at time k, given all the data through time k z super k, will be the sum of mu jk, Gaussian density argument x, mean x hat j, covariance pj. And these are the weights, and these are the probabilities coming out from base formula. And to replace this mixture with a single Gaussian using moment matching, you match the mean, match the covariance. What you do is find the mean of the mixture. X hat kk is sum of mu j x hat j. So the mean of the mixture is the weighted sum of the means, and the covariance of the mixture, as shown in 146, is a weighted sum of the covariances plus another term that is called the spread of the means. This is the outer product, x hat j minus x hat, this is the combined mean, times its transpose. So this is the spread of the means. The farther the means are from the combined mean, so these are the mode condition means, this is the overall mean, the bigger this term will be. And we do pay a penalty for this, but this is the penalty to be paid for summarizing the state estimate by a single mean and the covariance. So, under what conditions is this exact? It's very important to understand the assumptions of every algorithm, when it works and when it's not working, because in the real world we always have to ask ourselves the question, what are the limitations of the algorithm? Is the problem at hand amenable to a particular solution? So what we have here as assumption is that the correct model is among the set of models considered, and the same model has been in effect from the initial time. It turns out that assumption 1 can be considered as a reasonable approximation. However, assumption 2 is not true, definitely, if a maneuver started at some time within the interval 1k, in which case a model change or mode jump occurred. So what we have, and it is indeed remarkable that you can get away with a small number of models in many practical situations, but you cannot get away assuming that the same model stays with you. One interesting result that it's worth pointing out, if the mode set includes the correct one and no mode jump occurs, the probability of the true mode has been shown to converge to unity. That is, this approach yields consistent estimates of the system parameters. That's very important. So, in the long run, asymptotically, the probability of the correct mode will go to 1 and everybody else will go to 0. Now, if the correct mode is not within the mode set, then there will be a convergence to one of the modes nearest to the correct one. And there are some details in this particular paper published a number of years ago. Because the non-switching or the static algorithm is so simple, there have been a number of modifications that people have used to adapt the non-switching model to the case of switching models. They are ad hoc modifications, and they can be made to the static estimator to operate in the case of switching models. One of these is that an artificial lower bound is imposed on the model probabilities. Obviously, a renormalization of the remaining probabilities is needed, so sum of every probability is still unity. There is a problem, however, a shortcoming of this static multiple model estimator when used with switching models, even though with this ad hoc modification that the probabilities are subject to, the errors in the mismatched filters can go to unacceptable levels. Therefore, they are typically, again, a second heuristic approach. They are reinitialized, those which are mismatched, and this is accomplished by using the estimate from the filter corresponding to the best matched model in all the other filters. It should be pointed out that these are fixes, and it turns out that they are automatically built in the dynamic multiple model estimation algorithms to be discussed next. In other words, there is really no need in a dynamic situation to use an ad hoc modified static estimator.